examples. We're going to discuss accelerating and non-accelerating forces. So I'm going to give you guys a second to jot this down if you haven't jotted this down already. We're going to do 2 more and wrap this up. And then I'm going to give you guys the rest of this lesson, which should be about maybe 15 minutes at the end, just to work on motion 4 and motion 5. I haven't given you guys the answers to motion 5 yet. I'm probably going to put them up on the weekend because I'd like you guys to give a try of motion 5 first without having the answers available to you, and then give you guys the answers towards the end so you can correct your work and then fix mistakes you made. I don't want you guys to go straight to the answers every second. If you don't know how to do a question, just skip it for the meantime and then come back to it. And if you still don't know how to do a question, I just yelled at my physics students for this. If you still don't know how to do a question, you need to ask me or someone else how to do it. I have a little bit of an issue with, I can't believe I'm still telling year 11s this, but I'm always like this. If you're doing a question or a series of questions, and you don't know how to do a question, I used to yell at my year 9s this too. You need to ask me how to do that question. It might sound obvious, but it's just the amount of students that I'll go to correct their work and they're saying, oh yeah, I skipped question 4. I'm like, oh, why did you skip question 4? I didn't know how to do it. I'm like, well, that's the whole reason I give you guys questions. I give you guys questions for 2 reasons. The first is to practice the skills that I taught you. But the second is to find the holes in your understanding. You might not have understood something well enough, so therefore you can't answer a particular question. Now, if you don't get help on how to understand that topic, then you'll never learn how to do that particular skill. You'll never learn how to fill in that gap in that knowledge. And so therefore, what that means is that if you get that question on a test, you're not going to be able to answer that question because you never learned how to fill in that gap. Worse still is that if you then go into year 11 or year 12 and you've got that gap, and then it's like, right, I'm going to rely on you guys knowing this piece of knowledge because I'm going to build on top of it. You guys are going to be like, well, I never understood the first part of this in year 9 or year 10. How am I going to understand the second part of it in year 11, year 12? It's really important that if you don't understand how to do something, find out how to do it. Find out how to do the questions you have no idea. That might involve looking at the answers, it might involve asking me, it might involve looking something up on the internet or asking a friend, but don't leave questions unfinished. You should always try to find out how to do the questions that you don't know how to do. That's different, and there's also really nothing wrong with getting a question wrong. If you get a question wrong, that's really good. That means you've actually found one of these holes in your knowledge, so you know what you need to plug up. There are a lot of questions that I can't ask you guys, so therefore you probably still have, even if you get 100% on a particular worksheet, you still might not know one of the skills because I can't ask you every single question imaginable. So if you find a hole, then it's really good in your understanding. That's great because it means you can fill it. This is what we did last lesson. That it has to be the same size. You are screen sharing. Am I sharing right? Yeah, I am sharing that screen. That's cool. Remember, they must be, pardon me, the same size, act in opposite directions, but act on different objects. If they didn't act on different objects, then nothing would ever move because you would never be able to get an unbalanced force. We need to have unbalanced forces. And the reason we do have unbalanced forces is even though the action-reaction pairs might be equal, they're acting on different objects. So what we did last lesson is we looked at some examples of force diagrams. The first force diagram we looked at was we looked at in space where there is no force. Because in space there is no force at all, that means an object at rest will stay at rest. And an object in motion will stay in motion because there is no force. So that object, that green apple, is going to keep floating on forever. It's never going to stop. Then we brought our apples down onto Earth, and we said, well, what happens when we go to Earth? Earth is where we get some interesting things happen. We said there is a force of gravity pulls this apple down. And if there's a force of gravity that pulls the apple down, the opposite force will also have to be a gravitational force. And that pulls the apple upwards. That pulls the earth upwards. These are acting on different objects. Then you've also got this new force, which we call the normal force. The normal force is a force that the ground pushes up on the apple. Now, if the ground is doing the pushing, guess where the reactionary force is going to be on? It's going to be on the ground. So the ground is what gets pushed down. And so these forces of gravity and the normal force are balanced. Even though they're balanced, these two forces are not action reaction pairs because they're acting on the same object. But each of them has an action reactionary pair. We then did the next example is we looked at a bookcase. With the bookcase, we did the same thing. We did a normal force. We did another, and we did the normal force is the earth pushing up on the bookcase. The earth is, or the ground is going to push, the bookcase is going to push down the ground. That's why when you move a bookcase, you look underneath it, the carpet's all squashed. That's because the bookcase is pushed down onto the ground and squashed the carpet. At the same time, we've also got gravity. Let's do gravity in light green. We've got gravity here. We've got gravity. Whoops. Has to be in the opposite direction, doesn't it? Gravity is being, the earth is being pulled up towards the bookcase. We said that those forces, the force of gravity on the earth is very, very small. The acceleration of the earth is very, very small because the earth is so large. But then what we did was we decided to throw in a man. We said, right, I'm going to put a man in here. That doesn't make sense. He's got 3 arms. How do I fix this? There we go, that's a bit better. And we said that that man is going to have a push force. He's going to push on the, bookcase, and the bookcase is going to push back on him. In fact, you can use that bookcase as something to push away from. If you were trying to jump, like if you're trying to do a wall run or something, you could push against the bookcase. And then, of course, if you're pushing against that bookcase, guess what? You're applying a motion that way. You're probably going to experience some friction. And the friction is caused because essentially as you push forward, right, the earth pushes backwards on the bookcase. And that's because you're trying to push the earth forward at the same time. If you think about it, why is that the case? Those two things are rubbing against each other. So as you push forwards on the earth is going to try and push backwards. It's going to try and resist you pushing forwards on it. And those are all the forces acting on it. We should note that if the push force and the frictional force are equal, then you're probably going to, you might not get any motion, or you might get constant motion. Remember, if the net force equals 0, that doesn't mean that the objects are stationary. It can mean that there is constant motion. Now, what we're going to do today is we're going to ramp it up a little bit. We're going to talk about 2 more of these examples. So today's is to talk about 2 more examples. We will discuss accelerating and non-accelerating force diagrams. We're going to start off by talking about a non-accelerating force diagram. And I want to show you guys the girl on the bicycle. Now we're going to freeze frame here. And we're going to talk about this. We're going to talk about this girl. This girl on this bike has a constant velocity. She's not speeding up. She's not slowing down. So I'm actually going to draw that with a black arrow above her, not from her. And I'm going to write this down as a constant motion or a constant speed. Now, some of you guys are looking at this and thinking, oh my God, how do I draw this bicycle? This is how I would draw a bicycle if I was you guys. I would draw a box, I'll draw one wheel, I'll draw another wheel. There you go. There's your bicycle. Right, if you want to get a little bit more artistic, you could do this. This is how I would. That's how I draw bicycles. But yeah, and you can draw a person on the bicycle, whatever. But yeah, you need to draw a bicycle, but on this bicycle, so I'm going to draw a circle, circle, but not on the bicycle. Above it, we're going to draw an arrow here which says constant speed. Now, if we're going to a constant speed, that means there is no acceleration. So I'm actually going to do this as a dot point here. Constant speed means no acceleration, which means we've got no net force. We've got a zero net force. We've got zero net force, or you could say there is no, all the forces are balanced. So that's essentially what that means. No acceleration, no net force, all forces are balanced. So when we look at these forces that are acting on the girl, we're going to quickly see that all of these forces have to be balanced in order for her speed to be constant. So let's talk about some of those forces. And you know what we're going to do? Because we had such a hard time with the bookcase, we're only going to look on the forces acting on the girl. Okay, now I understand that these forces acting on the girl on the bike have other forces, have reactionary forces, but we're not going to draw those forces in. We're only going to draw the forces on the bike. So we can tell that because this girl is on Earth, there is always going to be one constant force, which is going to be gravity. I'm going to draw gravity in. I'm going to call that F of G. That's the gravitational force. And because we know this girl isn't sinking into the ground, just like every other time, I'm going to draw a normal force. Those two forces are opposite each other. They are not action-reaction pairs because they're both acting on the same object, but they happen to balance each other out because the person is not flying up into the air and they're not sinking down into the ground. These forces are balanced. Now there are two more forces that we should pay attention to with this rider. This rider is also going to have a force forward. Now that force forward is going to be the force caused by her pushing on the pedals. And that force forward is going to be essentially, we're going to call that force forward her push force. You might want to call this you know what, actually I don't like calling it a push force. I'm going to call it a drive force. This is her driving force. As she turns the wheels, as she turns the pedals, that's going to give her a drive forward. That drive forward is caused by the wheels pushing back on the ground, and so then the ground pushes forwards on her. But there is one more force acting on her, and that's going to be friction. And friction is going to be backwards. It always goes against the motion. And because it's a constant speed, we know that these two forces have to balance. So one extra little factor I'm going to add here is the drive force must equal the frictional force. Can someone tell me what would happen? I'm going to ask this to chat while you guys are copying this down. Can someone tell me what would happen if the drive force was less than the frictional force? What would happen if the drive force was less than the frictional force? Okay, want someone in chat to give me an answer here. Let's go towards the bottom. Thomas, have you got an answer? Sunny, Ryan, Ricardo, what would happen if the drive force, so the force that she's pushing forwards on the pedal, what would happen if that was less than the frictional force? Smaller than the frictional force. The frictional force is bigger. What would happen? The bike is not moving. Okay, if the drive force was less, you would see, and I like Eric's answer a little bit better. You would move slower. You would start to slow down. That frictional force would start to eat into your speed, and you would start to decrease. But yeah, if you weren't moving initially, if you were like stationary and you started to pedal with a drive force that was less than the frictional force, Leo, you would be correct. You would not move at all. Wouldn't you start going backwards? Well, here's the trick with frictional force. I will be honest with you. Frictional force is difficult. The frictional force never causes, only opposes motion. It never actually makes something go backwards. You can never like use friction to speed up moving backwards. You can only have friction slow you down. Okay, next question. What would happen if the drive force was more than the frictional force? If your drive force overcame the frictional force, was greater than the frictional force, tell me what would happen.
The bike would accelerate.
She would accelerate, correct. Thank you, guys. Yeah, she would start getting faster and faster and faster. She would start to speed up. The faster she got, she would probably start to experience air resistance and other things. But essentially, yeah, she would not have a constant speed. She would get faster instead of being slower. But at this type of situation, she's got a constant speed, and that's the case. It's actually kind of interesting how easy it is. I always think about this, and I know this is weird, but I think about this and I think, man, to balance these forces out must be really hard. Like to balance out the force of friction against your force of your speed must be hard to figure out, but actually it's not. Like if you think about it, you don't see bike riders going, oh man, a pilot's pedaling too quickly. They can just adjust their push force to make sure that they can travel at a constant speed. They'll push a bit harder on their pedals to go faster, but then when they're done pedaling with speeding up, they can keep that same speed quite easily. And it's a thing with humans that when you look at it on paper, man, trying to match those two forces must be really hard. But when you in practice, it's actually humans are pretty good at it. So it's something to think about. All right, we're going to go with one more diagram, and that's going to be this diagram here. I'm going to change the slide to our very last diagram, which is going to be the apple. Now this apple of frozen in time right here is falling towards the ground. Okay, it's actually accelerating towards the ground. So if I say this is accelerating towards the ground, what does that mean? If I say this is accelerating towards the ground, what does that mean the net force is?
Downward force is greater than, actually no.
Yeah. The net force is downwards. Now we don't know how much that net force is downwards, we just know that it's downwards. So let's look at the forces acting on the apple. Well, the forces acting on the apple is we've got a gravitational force. And then that's roughly it. You might say, well, what do you mean that's roughly it? It's like, well, it hasn't got an upwards force because it hasn't got the normal force. There's no way you can get an upwards force on this because it's not pushing against anything. You could say technically, yeah, there would be air resistance, but we're going to ignore air resistance. That's what the only force acting on the apple. And because that's the only force acting on the apple, that's why there is a net force. Because there's only one force acting on it. Now, if whereas when the apple is sitting on the ground, there is also a force upwards, which makes the net force equal to 0. When that thing is accelerating towards the ground, there is a net force, and that force is just gravity. This seems like a really weird one to have at the end, but I like to put this one here because I want to show you guys against, I guess this is what we would refer to as an unbalanced force. And that's, yeah. So those are actually all the force diagrams I wanted to go through with you guys. Now, we could go through force, what happens if these forces are not, we're not going to go through dealing with these forces when they're not at perfect right angles, because that would become very, very difficult. We're not going to try and calculate the net forces the same way that we did at angles that I showed you guys as an advanced thing. I'm just going to expect you guys to know these basic ones. We're not going to talk about tension and compression forces, but we could talk about that. But yeah, I just wanted to stick to just some of the basic forces here. But that is all I have time to talk to you guys about, and that's all that I wanted to talk to you guys about. So what I'd like you guys to do now is, that's right, Everest, you did miss out on the lesson though, unfortunately, is I'd like you guys to work on motion 5. Again, reminder, I'm not going to give you guys the answer to motion 5 until at least Tuesday, just to give you guys, or maybe on the weekend, just to give you guys a chance to try some of those questions. But I'm going to now do this. I'm going to say to you guys, if you want, you guys don't have to stick around. You guys can leave if you want and work on motion 5. If you want to stick around and if you need some help, you are more than welcome to ask for some help now. I will be around here for the next 10 minutes, giving some people help if they ask for it, but you don't have to. If you want to head off, that's okay. Have a good weekend if you do head off. Make sure you submit motion 1, 2, 3, and 4. If you have got them, motion 4 is due today. So you make sure that's submitted at some point today, so I can start correcting it. I've started to correct motions motion 3, but I haven't finished correcting motion 3 yet, but I'm going to start going through that today. So correcting motion 3 and motion 4 today. So that's going to be what I'm going to be looking at. Otherwise, take care. So I'm going to be here if you guys need some help. Okay, Everest, the lesson was about, I will quickly open this back up just because you missed it. I'll quickly go through the two. We only went through 2 slides, so it was really quick. What we did was we went back over talking about this stuff here, but the bulk of the lesson was talking about, we talked about this girl. This girl experiences a constant speed, and because she's got a constant speed, that means we know that she has no acceleration. Constant speed means no acceleration. Otherwise, she'd speed up and slow down. No acceleration, F equals ma, that means that A is, the force is 0. There is no force. So all forces must be balanced. So then we talked about, well, what forces could possibly act on her? We've got the normal force, we've got the gravitation force. These forces are in opposite directions, they're balanced. Then we've got a driving force, which is her pushing on the pedals, and a frictional force, which is the earth pushing back on her. Those forces have to be balanced because she's got a constant speed. We said that if the drive force was more than the frictional force, she'd speed up. If the drive force was less than the frictional force, she would slow down. But I can actually say that I know this is true because I know the net force equals 0. That's what we did first. Would wind resistance be a part of the force? Yeah, wind resistance would be part of the net force. It would be part of the frictional force. However, most of the time we're going to neglect wind resistance. The reason we neglect wind resistance is because it doesn't play a huge role for slower moving objects. And also because when we're studying physics, we want to keep, and engineering, we want to keep these things simple. So that when we do create objects, we want to try and I want to teach you guys without air resistance now. Then later on, if we do need to deal with air resistance, we can build that into a question. The next thing we talked about was an apple falling down in the Earth's gravity. This time, the apple is accelerating, which means we know there is a net force. And the next thing we also know is because it's a net force, we know there is an unbalanced force. So then we started to say, well, what was the unbalanced force? In this case, the unbalanced force is the gravitational force. When that object is sitting on the ground, there is a normal force. But when that object is just falling in Earth's gravity, there is no normal force. It just falls down, it keeps falling. So that's why we refer to this as, that's why we say there is a net force in this case. It is the gravitational force which is pulling downwards. You could say there could be air resistance on the apple, but there's probably not much because, again, it's an apple. It's a very small thing. And then that was it. That was all that we talked about, really. We went back over the stuff that we talked about last lesson, and then we just talked about these two things. So, yeah, and then we also went through the attendance question, which I said is not an example of Newton's third law, because in the attendance question, the skydiver had a net force upwards, which is caused by drag, but these forces happen to be equal. But even though those two forces happen to be equal, they were not action-reaction pairs because they're acting on the same object. So it's not an example of Newton's third law. They have to be acting on different objects. Obviously, there is an action-reaction pair on this object. We didn't draw them in, especially for the bike rider. So the reason we're not going to draw all the action-reaction pairs in is because there's so many of them. We've got 4 forces acting on the bike rider, and each of those 4 forces has a reactionary force. There is the ground getting pushed down by the bike. There is the earth getting pulled up by the mass of the bike. The drive force is going to have a force against it on the wheels, and the frictional force is also going to be acting on the wheels in the opposite direction because of the ground. It's just, we're not going to deal with all of the forces here. We just looked at the forces acting on the bike rider. Does that help? That's all we went through anyway. And then I said start working on motion 5. So yeah.